All right, so today I'm going to talk a little bit about the PGL2 F4 theta correspondence. And so this will roughly fall into two pieces today. So today, the first thing that I'll do is just set up some preliminaries. So in particular, we'll have to go through some exceptional group constructions. And then I'll just go over some basics of the theta correspondence, very rough idea of what it is and what we plan, what we'll be doing today. So this is all general stuff. And then in the second part, we'll actually go through some aspects of the PGL2 F4 theta correspondence. And we're going to focus on two main parts. We'll talk about lifting principal series from PGL2 to F4. We'll also talk about the spin 9 distinguished representations of F4. Okay, and so this will connect this exceptional theta correspondence to the relative length program. So let's make one quick note. We're going to be skipping over a very important aspect of this exceptional theta correspondence. So there's sort of two parts. So this PGL2 F4 theta correspondence really falls into two parts. Sorry, one second. Roughly speaking, it has two parts. So the first is some analysis involving the Fourier Jacobi functor. And Heisenberg parabolics. And the second is sort of an analysis involving, let me just say the Siegel parabolic. So these two steps, these two parts are both important in their own right. Today, we're really just focusing on the second part. So I'm leaving out a whole lot of the story. And I'm focusing on the second part because this is the one this is the one that's related to the spin 9 distinguished representations more directly. And it's a little bit technically easier. So I think it will be more appropriate for this lecture. Oh, and let me also say, because I won't go through all of the details. Oh, what have I done?
OK，我以为就是随便做一个，我也没有啊，那行。
How do I get out of precision mode? Oh. fine. Oh, yeah, good a guess as any. Nope. Okay, maybe I'll just stop the screen sharing and then come back and yeah. And,
Oh no, this is the not the image. I bet this is the
oh,
this guy.
okay, hold on. I think my hand hit one of these buttons by mistake.
Oh,
Oh, okay. There we go. Oh, sorry about the technical glitch. Let me. Oh, yes, okay. So I'm not going to be able to go through all of the details of everything. Let me just write down the reference for this work, which is joint with Gordon 7. So I'll refer to this as just write KS. And this is my work with Gordon 7. We have this up on the archive. And it is called the dual pair. PGL2 cross. Nope, that is not what it's called. C cross F4 P allocates. So everything I described today, this is all joint with Gordon 7. All right. All right, so last time we talked a little bit about composition algebras and G2. We're going to need yet another exceptional algebraic structure today. This is the exceptional Jordan algebra, cubic exceptional Jordan algebra. I'm just going to list some of the important properties associated with this. We won't go into so much detail, but let me begin. Okay, we're going to have a field K, and we need the characteristic of K to be neither 2 nor 3. We'll also have some composition algebra, which we discussed last time. Over K. Okay. All right, and then we'll define this Jordan algebra, which will depend on the composition algebra. As a set, this is just going to be 3 by 3 matrices of the following form. They're going to look like Hermitian matrices. The diagonal entries, the Cj, these will be coming from our field, but these off-diagonal entries, xj, these are going to be coming from our composition algebra. All right, so we have these skew Hermitian matrices. This is a K vector space with just the usual additive structure on 3 by 3 matrices. This is an algebra, so it's going to have a multiplication. And here we get the first usual thing, the multiplication is given by the skew commutator. So if I take, let's say, x and y in J, we'll define a product. I'll use star for this product. Okay. And it's going to be defined as x times y. That's going to be the usual matrix multiplication, plus y times x. So this Jordan algebra also comes with a cubic norm, which is going to be a map from J to the base field K. So if we have an element of our Jordan algebra, I'm not going to write down the formula for this, but this thing basically looks like the determinant of the matrix X. Now you have to be a little bit careful about this because the composition algebra may be non-associative, but there is some, you can sort of write down a formula. It looks very much like the usual determinant for a 3x3 matrix. Okay, we won't need the formula, so let's skip that. And I also want to say that this is multiplicative, just like the determinant. A Jordan algebra also comes with a trace. Let me use the coordinates for an element of J that we have above. So in particular, C1, C2, and C3, these will be the diagonal elements in that matrix. And the trace is just going to be the sum. This is C1, C2, plus C3. Okay, so for some details, here are just a few references, because I'm not going to say too much. Okay, so you can look at the Book of Involutions. And Pollock has some very nice notes. Schrodinger book. Okay, now one of the most important things for our discussion is that this Jordan algebra, this has a notion of rank. Oh, sorry, I need to say one more thing before that. Okay, so in the Jordan algebra, there's also a notion of adjoint. So this is a map from J to itself. Call this upper sharp. And again, this is going to look like the formula for the adjoint of a 3x3 matrix. Okay, now I can talk about the notion of rank. And this is the one that's going to be quite important for us today. All right, so the first thing that we can say is that all elements of J, they have rank less than or equal to 3. X in J has rank less than or equal to 2. We'll sort of define this as being when the norm of X is 0. Backward. two bullets. Okay, for x and j, the rank is less than or equal to 1. This happens if and only if the adjoint is 0. And then finally, the rank is 0 if and only if x is 0. Okay, so you can take this as the definition. All right, now we have some natural groups which are acting on the Jordan algebra J. So let's define HC. This will be pairs of elements G nu, which are in GLJ cross K cross. Okay, and these will be those elements that scale the norm. So the norm of Gx is nu norm of x for all x and j. It's sort of the similitude group. All right, and inside of this, there's the subgroup of elements. Sorry. I'm just going to look at the subgroup of elements where nu is equal to 1. All right, so we have this action of HC on J. And the orbits, at least over the algebraic closure, are parameterized by rank. Let me make one other remark, general remark about these Jordan algebras. Okay, so last time we proved that G2 is the automorphism group of the Octonian algebras. F4 has a similar realization. Write this as a note. F4 can be realized as the group of automorphisms, the K algebra automorphisms of a Jordan algebra, where the composition algebra is an Octonian algebra. All right, and let me make one final comment. This automorphism group, this sits inside of HO1. So that norm preserving group, and this norm preserving group, this is a group of type E6. So once again, if you want to understand these isomorphisms, you can take a look at Springer-Veldkamp, for example. The one thing that I do want to mention is that the proof in the case of F4, it follows a similar strategy to what we looked at when we were looking at G2 last week. The relevant homogeneous space in this case, this is the primitive idempotence. So instead of, last time we had this notion of special pairs in a composition algebra, and this gave us a lot of information about the structure of the automorphism group. For a Jordan algebra, we can do something similar, but now the object to look at is primitive idempotence. All right. Let me be a little bit careful. So I believe this is true over the p-adic. Let's see. The context. Yes, it should be true in general that the different forms of the composition algebra will result in different forms of F4, and you should be able to pick up all of them. In the case of p-adic fields, we'll have just a single Octonian algebra, and so there's only one form of F4 over p-adic fields.
This is also the characteristic of the theater.
this I would have to be more careful about. Okay, so as long as you avoid characteristics 2 and 3, then I believe everything should be the same. I know less about global fields, so maybe I won't say anything. All right. Other questions? Sorry? What about E6?
The same question is I think the different form for the.
Oh, yes, yes. Yeah, so you'll be able to pick up different forms of E6 as you vary the composition algebra. Again, it should give you all of them. Yeah. Oh, okay. Okay, so now I want to discuss two constructions of exceptional groups. And I guess let me specifically do this in the context of E7, but these constructions are more general. All right, so okay, so first we'll look at Titz's second construction. Okay, so once again, I'm not going to go through any of the details. Let me just sort of present some aspects of the construction. So the input for Titz's second construction is a composition algebra. J, a Jordan algebra. And the output is going to be a Lie algebra. Let me call this G sub C comma J. Okay, and this is defined, let's just say as a vector space first. This is going to be derivations of the composition algebra plus derivations of the Jordan algebra plus we'll have C0 tensor J0. So these are both just the trace 0 elements. Okay. All right. So the important part of this construction is that you can give GCJ the structure of a Lie algebra. And in particular, this extends the natural action of the derivation subalgebras on the trace 0 elements. Okay, in the case that we're interested in, so for C, a quaternion algebra, and J, this exceptional Jordan algebra over the octonions. In this particular case, this GCJ, this gives us a form of E7. And this depends on the composition algebra C. And maybe at this point, be careful. Let me at this point say that we're already working over a p-adic field. Why this construction is so important for us is that this gives us a dual pair inside of the Lie algebra. This is a dual pair. And so let me also say the Lie algebra dual pair this gives us a dual pair at the level of the groups. And at the level of the groups, what we find is that we have the automorphisms of the composition algebra cross F4 sitting inside E7C. And for us, we'll just take this to be the adjoint form. One remark, over the p-adic field, there's a single isomorphism class of octonian algebras. And so in particular, there's only a single form of F4, the split form. So this is always split. Yes, that's right. I mean, in this case, the C and O are different. Yeah. When I say octonians, I specifically mean dimension 8.
Yeah.
Okay.
I mean, thinking like over the number field, you can have like two different splitting field, right? For C and O.
Oh, sure. Yeah, I mean, in Titz's second construction, the C and the Jordan algebra, these are distinct inputs. Yeah. Okay, so this gives us one realization of the dual pair that we're going to be using for the exceptional theta correspondence. All right, now let me describe a second construction. Okay, this is due independently to Cantor, Coker, and Titz. All right, so let's see, maybe. Okay, so let me describe it this way. So we're going to start with the E7 Lie algebra. All right, and so inside of E7, we have a parabolic, the E6 parabolic. Okay, and I'll write N for the unipotent radical of the parabolic. So here is our parabolic subgroup, our parabolic subalgebra. Unipotent radical N. And then we also have the opposite. Okay, the thing that's going to be important for us is that N can be identified with the Jordan algebra over the octonians. So the unipotent radical admits the structure of a Jordan algebra. Okay, and then let me just make one very quick comment about the compatibility of these two constructions. So maybe there are two facts here. The first is that up to conjugacy, the map of SL2 plus F4 into E7 is unique. Here I'm working over the algebraic closure. Second thing I want to say is let's actually, let me just scroll back. Let's take a look at the second construction. This is sort of E7 built out of the E6 parabolic. Okay, once we identify this Jordan algebra structure, we can sort of use this to calculate the centralizer of F4. So we have F4, which is sitting inside of E6, which is inside of E7. So we're thinking of this E6 as the parabolic, the E6 parabolic. This is part of the levy. You can compute the centralizer of this F4. It's going to be three-dimensional, and maybe I'll just write it like this. It's the center of the levy plus k times the identity. It would be the identity element of J O. And let's say that this is the one that's sitting inside of N. And then there's a J O, sorry. There's the identity sitting inside of the dual. And this is inside of the opposite unipotent radical. And this is isomorphic to SL2. So this is how we can see the dual pair in the second construction. All right. I'll call this the KKT construction. All right. Okay, now let me say just a few very basic things about the theta correspondence, what the goal of a theta correspondence is, and then we'll actually get into the exceptional theta correspondence. All right, so now K is a p-adic field. G will be split F4 over K. H is going to be PGL2. Okay, so maybe let me just say, so throughout, we had this composition algebra C running around. For today's discussion, we're just going to take this to be the split quaternion algebra. And so in this case, the dual pair is PGL2 cross F4, sitting inside of a split E7. And I'll use a script G for this E7.
The E7 with the condition restricted to the blue here, would it be like E7 have the smallest one is, I guess, 56.
Oh, your question is if you take the 56-dimensional representation of E7 and you restrict it to the dual pair, what does it look like?
4.
F4 has a 26-dimensional representation, which is this trace zero part of the Jordan algebra, which has 27 dimensions. Sorry, say again.
Cannot have the PDL2 tensor with F4 dimension is the problem of PDL2 part is true. Yes. The probably useful.
We can talk maybe more at the end.
Yeah. It's a very technical.
All right. So here's a fact. There's a more general thing going on here, but this G, this group of type E7, this has a unique, irreducible, unitary minimal, well, okay, let me say that it's minimal representation. I'll call this pi, and then early V. Let me just make a few remarks. So this is unitary. It has Iwahori fixed vectors. And, oh, so only two, right? It's minimal. Sorry, let me say what I mean by minimal. So, yeah, right. Oh, I didn't define pi. I'm just saying it. Yeah. So, yeah. So,
You see the Piaget case, E7 is always lethal.
E7.
It's not.
No, the E7 doesn't have to be split.
Yeah.
So if we took the non-split quaternion algebra, we have a non-split form of E7.
Yes, so you only consider two-fold.
There are only, over a p-adic field, there are only two forms of a quaternion algebra. There's the split and then the division algebra. And so there are two forms of E7.
That's the only two used.
Yeah, so that's the only
That's
two.
the only two-fold, yeah.
Yeah, that's right. And today's discussion, this will only involve the split form. Right, okay, so I wanted to say, just very briefly, I don't want to define minimal too carefully, but, say again? Now I'm just focusing on p-adic fields, yeah. Okay, so let's say that so a minimal representation, this will be one with a Howe-Harishchandra local character expansion. That out. That's supported in the closure of the minimal orbit. Nilpotent. We're going to take as a black box a result about the minimal representation that will, that's going to be the thing that we primarily interact with. So we won't need to worry about the specific definition of the minimal representation.
Ed is talking about the minimal subject to the minimum algebra of the E7. Yes. And your talk is given yesterday the theorem you did for the E6. Yeah, this is the geometric representation like the computations for this minimal orbit. The analogy of the theta the wave representations for the minimal orbit of the SP.
Right.
Just talking about this is the minimal orbit is from the Grassmannian.
Relate to unconditional way. But this is true in the more just.
The next one is for the proof by for the E6, E7 and E8.
All right, so now we have this minimal representation. We're going to use this to construct a correspondence in the following way. So let's take tau to be a smooth, irreducible representation of PGL2, which I am calling H. So H is PGL2. Given our minimal representation, we can consider, I'll call this V lower tau, and this is just going to be the maximal tau isotypic quotient. All right, so this definitely admits an action of H, but this also admits an action of G because this is because G is the centralizer of H. And so because of this dual action, we can factor V sub tau as tau tensor something. We'll call this something theta of tau. So this is referred to as big theta. And just to be very explicit, so we have this product acting, the H is acting on tau, usual fashion, and the G is acting on theta of tau. So theta of tau is a G representation. Okay, now one other point. We can also define so-called small theta. And this will be the maximal semi-simple quotient. Of the G representation big theta. This is sometimes called the co-circle. Okay, and so now what's the goal? So first off, the theta correspondence gives us a way of taking a representation of H and constructing some representation of G. And so in our particular case, we're taking a representation of PGL2. These are things that we understand quite well. And out of that, we're producing representations of F4, which maybe we don't understand as well, which I definitely don't understand as well. Okay, but this gives us some way to get at them. Okay, and so in particular, the goal will be to describe, and I'll be a little bit vague here, describe both big theta and small theta for tau in an irreducible smooth representation of PGL. It's also worth pointing out that you can turn everything around. You can define, if you're given some irreducible smooth representation of F4, you can do the same construction to produce representations of PGL2. That's important. We discuss aspects of that in the paper, but I don't want to talk about that today. Let me just give you an example. Sort of the types of things, the types of results that you might be interested in. So here's one of the results from my paper with Gordon. Oh yeah, you take a tempered representation. You take a tempered representation of PGL2, then big theta is irreducible, and it's so then it is equal to small theta. All right, so I want to start talking about some aspects of this exceptional theta correspondence. I want to introduce two of the basic tools that we're going to use in today's discussion. One is fairly straightforward. Let me just think for a moment what. Yeah, okay, I should write this down a little bit carefully. Okay, so let's take tau, an irreducible representation of H. And let's let U contained in H be a unipotent subgroup. Could be trivial. And let's say that we have a character psi. One more thing, let's let S be the stabilizer inside of regular G. So inside of S. Okay, so now this first tool, this is a formula for the coinvariance second, what am I saying? Oh, no, okay, sorry, I wrote something incorrectly. The U, we want the U to be inside of G. We're starting out with an H representation, but then unipotent subgroup inside of G. Okay, now we want to understand big theta of tau. Okay, and so one way to do that is to compute various coinvariants. Okay, so we want to understand this thing. We can't get at this directly, but in fact, there's a nice formula for it's the linear dual. So the linear dual of the U psi coinvariance of big theta of tau, this is isomorphic as S modules to the Hom space of H invariant maps from the coinvariance of the minimal representation to tau. This is not so difficult to prove, but let me skip over it just for the sake of time. Okay? All right, so the first tool, this is just about a way of describing linear dual of covariance. And I also just want to point out that we can take U to be trivial. Okay, so in other words, this also just gives a way of describing the linear dual of big theta. Now the second tool. This one is basically, this is sort of like a partial Schrodinger model for V. Yeah, for the first tool, it works in both orders. So you can start with a,
The U here is arbitrary uniform or
a little bit careful. Yeah, I think it's arbitrary. For us, it will just be some unipotent radical of a parabolic. Yeah, sure. Okay, so the second tool, this is a Schrodinger model for the minimal representation. But unlike in the case of the Weil representation, we don't at the moment have a sort of a full model. This is only valid on a maximal parabolic subgroup. And the one I'm going to describe is on the Siegel parabolic. Which in our case, this is the E6 parabolic. Okay. Okay, so I think this was first done in Savin's Inventiones paper from '94. Okay, so. And again, it's done in more generality, but I'm just specializing to the case of E7 for today. So the minimal representation, this has a P, let me write it with P opposite. I'll define that in just a second, filtration. What is this? This is going to be the E6 parabolic. Say that this has a Levy factorization m times n. So we're going to give a P bar filtration. It will look like this. So we have our minimal representation, okay? And then we have a surjective map onto the n covariance. And the kernel of this map is a space of smooth, compactly supported functions. Where do these functions live? They live on this space omega, and this, oops, this is the set of rank 1 elements in JO. Okay, but remember from this Cantor-Coker-Titz construction, the unipotent radical of the E6 Levy, this can be identified with the exceptional, the 27-dimensional exceptional Jordan algebra, this JO. Now I just need to make sure that I'm doing on the correct side. I said a P minus filtration, sorry, so this should be N minus. And this one should be N. Just to say this point again, we're over a p-adic field, and so there's only one form of octonions, the split octonions. Yeah.
Also have the not have a better understanding of the idea of the questions. There
is ongoing work about trying to figure out the action of the Weil elements in terms of some. So in the classical Schrodinger model of the Weil representation, you have this fairly nice action of the Siegel parabolic, which is going to look exactly like what I'm going to write down in just a moment. But then there's, in terms of generating the full group, there's one extra element that you need. It's a Weil group element, and it acts via Fourier transform. So it has been a long-standing problem to try and take this Schrodinger model for these sort of more general minimal representations on simple lace groups or exceptional groups, and try and understand the full action of the group. And so it's always been expected that there should be some Fourier transform-like thing. And I know Nadia has been working on this for a while. WeTech also, and I guess touched. So there's ongoing work, but I don't know the current state. I am not personally working on this. No. Okay, so we have this filtration, but let me make this a little bit more precise. And I can do this in two places. Let me think about what we need. Oh, yeah. Okay, so so if we take an element in the levy and an element in n minus, F in this space of functions, right? How does M act on F? This is essentially the geometric action. But in fact, there is some character. Let me see if I wrote this down. This determinant, this is coming from the action of M on N. This one should be coming from the action on N minus, but maybe I would want to double check that. All right, and we can also describe the action of the unipotent radical. Ooh, sorry, let me go back. Always forget to write this down. So we need to first fix an additive character. A non-trivial additive character. So that's part of the input. We see that in the action of the unipotent radical. And so it multiplies the function by a character in the following way. And now I find out if I'm labeling things correctly. X is in N. Okay. N is in N minus. So this pairing is coming from the killing form. And when you identify, right, this will become relevant later. When you identify the Jordan algebra with N and N minus via the trace pairing, then this is just the trace of the product. Okay. All right, so this gives us a description of the Siegel parabolic acting on the kernel of this filtration, the smallest element of this filtration. This is pretty explicit. And then finally, let me just describe the space of co-invariance. So this will be the minimal representation for M. We'll set this up. We can set this up so that the center acts trivially. Okay, and so the action of the center is going to be encoded by some character chi1. And then there's also a one-dimensional space, some other character chi2. These are characters. All right. Pause for a moment. Any questions?
Basically also from the inducement of this parabolic.
Sorry, say again. Yes.
My question is, this is also continuous from the parabolic induction from this. I was trying to see which consequence is coming from which principal series. Can you construct that or no?
It is, I know where to look for that for you. The minimal representation will be a constituent of a degenerate principal series. I'm forgetting which one it is off the top of my head right now. But we can definitely look that up.
So it's from the, if you take from the parabolic from the E6, on the E6 part of the you put the minimal within the you are not putting the trivial. Otherwise, that become very.
I mean, it can be realized in terms of actual degenerate principles, constituents of degenerate principal series. And so in that case, you're just inducing from a character.
Oh, but for which parabolic?
Yeah, this is what I'd have to.
E6 parabolic?
Let's talk about it after.
Calling back from 10.
Oh,
Yeah.
this here? Sorry. Okay, that's just bad notation. Let me just yeah. No co-invariance there. Let me. Yeah. No. That was just very bad notation on my part. So that's just it's. We have the levy M. It has some associated minimal representation, and that's exactly the thing that's appearing now. So now let's discuss how to lift principal series from PGL2 to F4. Okay, so we have our group G. This is E7. And let's say that we pick out some, let's fix some Borel. Okay, and then we have our Siegel parabolic, the E6 parabolic. Okay, and then from this we can get a Borel for F4. The Borel for PGL2. Okay. Okay, so in my work with 7, we can explicitly describe both big and small theta for all of the constituents of all of the irreducible constituents for principal series of PGL2. Today, I want to just focus on one aspect of the computation. And maybe let me write this out. So let's let I be a character of T sub H. This will be a maximal torus in B. Such that this is not in S, which is some explicit set of two characters. Basically, the point is that away from this set of two characters, things will work very nicely. And then for these two, you need to do some more refined analysis. If pi lives inside a principal series, we have an irreducible, an irreducible submodule of the principal series. And I'm using normalized induction for the principal series. Then big theta of pi is a quotient of a degenerate principal series for F4. So this Q, this is the B3 parabolic for F4. This omega 4, this is the fourth fundamental weight. Or maybe I'll say the fundamental weight non-trivial on the degree 1 short root. The F4 thinking diagram. All right, so just to recap the statement, we're taking some irreducible submodule for a principal series of PGL2, and we're going to show that the big theta is a quotient of a degenerate principal series. So in particular, this will give that the big theta is finite length, which is always an important step in setting up a theta correspondence. Okay, all right, so let's sketch the proof. Okay, so we want to understand big theta of pi, okay? And so from tool 1, we have some information about the linear. We know that this is isomorphic G modules. So the linear dual of big theta, this is a Hom space. Okay. And now pi sits inside of a principal series, and so we could compose by that injection. And we can look at H equivariant maps from V to the principal series. Okay. So our first step is actually just to understand the H module homomorphisms from V into a principal series. So now we're going to study this. Let me say it like this. Okay, so what we're going to do is we're going to apply the functor Hom H into the principal series, the P opposite filtration of V. Let me quickly go back up. So we have this exact sequence over here. We're going to apply this left exact functor, and so we're going to get a long exact sequence. We'll analyze the long exact sequence. This is going to reduce this Hom space in terms of the minimal representation, which we don't understand very well, to a Hom space in terms of the space of smooth functions on rank 1 elements. And this is something that we can get at more directly. So we're taking this functor, we're applying it to the exact sequence to get a long exact sequence. Get a long exact sequence. Maybe let me call the terms A, B, and C in this sequence. Okay. C. Let me not write out the long exact sequence, but there is a long exact sequence. And now let's look at the terms involving C. C was the n minus coinvariance. And we knew that this was isomorphic to minimal representation for M times some character plus some other character. Okay. All right, so we want to look at Hom H C induced representation chi. Okay, we have an induced representation we can apply Frobenius reciprocity. I'll write R sub B for the normalized functor of coinvariance. Okay. Now, this functor of coinvariance, right? This is taking coinvariance with respect to the unipotent radical of PGL2, but that lives inside of N in N opposite. Or maybe I wrote it. I'm sorry, maybe I need the opposite on the B's as I've defined things, but the point is that the unipotent elements, the unipotent radical of this Borel, this is going to be contained inside of N minus. And so this doesn't change. This is just V N minus. This TH is this is contained inside of M. That's the center of M, in fact. And so we know that this is Vm. Center is acting trivially. Chi1 plus chi2. All right, now I've lied a little bit, and let me just go back and adjust things very. We need some modular character coming from the normalized induction. And so in particular, this chi prime and chi double prime, we have to multiply by some other character. But the important thing is that this is always going to be 0 when chi is not equal to chi1 prime and chi2 prime. And so this is it's going to be exactly the center of M.
the something of the geo actor.
Yeah, that's right.
Yeah, that's why we have.
Actually, let me even write that here. All right. So in our long exact sequence, the Hom term associated to C, this is 0, as long as we're outside of this finite set of two elements. Similarly, the associated X term is also going to be 0. Writing it with T, so I'm put it down here. Okay, so from that long exact sequence, we get that let me write exactly what I said before. So from the long exact sequence, the term involving the minimal representation, that's B, the one in the middle, this is going to be the same as the Hom space for the term, the A term, and that's exactly our smooth, compactly supported functions on the rank 1 elements of the Jordan algebra. And let me apply the Frobenius reciprocity. This is the thing that we talked about. So now we're going to compute this. And so we're going to take a look at I'm going to take a look at this space of smooth, compactly supported functions on the rank 1 elements. We want to take the co-invariance. Let me forget the normalization for the moment. We just want to compute the UH co-invariance. This is the unipotent radical B. Okay. Okay. There are some standard techniques for computing co-invariance of these spaces of functions. Maybe let me just state this, and if you'd like to hear more, or I can give you a reference after. Okay. This can also be realized. As a space of functions. Let me come back to that point in a moment. This can also be realized as a space of functions on W0. What is this? These will be the rank 1 trace 0 elements in J. And this isomorphism will be as TH cross G modulus. So for details on this isomorphism, you can see Magard, Savin. They have a paper in Compositio. It's 97. So the next thing we want to do is we want to try and realize this space of functions as a parabolic induction. So the first, oh, oh no, there we go. Okay, so the first thing is that, in fact, omega 0 is a homogeneous space. Let me write this out. PH cross F4 acts transitively. On omega 0. Okay. A reference for this is Oshbacher. In a paper in Inventium from 87. Oh, and in particular, this is in section 8.6. Okay. All right, so in particular, so we have this space, rank 1, trace 0 elements. We have this transitive action. It will be a quotient of TH cross F4 by the stabilizer of some element. So let's fix. Okay, so in particular, we'll need to know what this stabilizer is. Say again. Omega 0 is, so we have our Jordan algebra. The trace 0 elements in the Jordan algebra is the 26-dimensional representation of F4. And then we can look at the orbit structure. I should be a little bit careful. Okay, let me say this. So we have the Jordan algebra, and we had the notion of rank from the beginning. And if you look at sort of the action of the norm scaling elements, then the orbits are classified by rank, at least over the algebraic closure. So this omega 0, these are the elements of rank 1 inside the Jordan algebra, but also trace 0. So rank 1 and trace 0 inside the Jordan algebra. Actually, let me flip the order here. Let me come back to the stabilizer. We can do some general things first. Okay, so we have our compactly supported smooth functions on, started writing, on the space of rank 1 trace 0 matrices. We can define an isomorphism to an induced representation. We take some function on this space, and we define a function on TH cross G, which sends T comma G to F of G inverse X naught times T. And so again, you can think of this, all of this is happening inside the Jordan algebra. Oh. All right, we need to include a character here. And if you include this character, then this becomes a TH cross G modulo homomorphism, isomorphism. And then we need to figure out what is the stabilizer. Okay, so here's the important point. We have omega zero, which is sitting inside of the trace zero elements in the Jordan algebra, and these are the rank one elements. This J0, this is an irreducible representation of F4. Irreducible highest weight representation with highest weight omega 4. The character which is this is the character which is non-trivial on, or it's the fourth fundamental weight, the one coming from the degree 1 short root. Okay, so viewed from this representation theoretic perspective, this omega 0 can also be viewed as the elements of this space such that X is a highest weight vector for some Borel. Okay, so then in particular, let's first look at the stabilizer, not of X naught, which is in this space, but let's look at the line, at the stabilizer of the line. So this is going to be TH cross Q, and this will be the B3 parabolic. We're getting that B3 parabolic just because the highest weight of that representation was the fourth fundamental weight. I'm sorry. Let me. That would include the compatibility. Both of these elements are going to scale X0 under this action. And so we need, however, T is scaling, if you're going to fix, I'm sorry, hold on, what did I write? Oh, sorry, no, what I wrote before was correct. No. So the stabilizer for the line is the full TH cross Q. Okay, but if we want to actually fix X naught, then we need some compatibility between the character and the action of the terms. This Q here? Yeah. This is the B3 parabolic for F4. So you remove, say again?
The maximal one.
Maximal, yes. Remove the degree 1 short root. Yeah. With the zero orbit, let's see. Yes, you have the zero orbit. Sorry, what's your question?
My question is, this is the zero. Basically, the question I want to ask is, if you consider new cone of this 26, is a new orbit?
Let's see. So we have rank 0 through 3. The rank 3, this is the open dense coming from the non-vanishing of the norm. Yeah.
All the genetic quality. You have infinite of that.
That could be right. Yeah. So the rank classification, this is with respect to this much larger group acting Yeah, that's right.
This is the rank one, right? The omega zero is
We're looking at rank one.
and you have also have the rank
Two.
oh, the guy.
Oh, okay.
Yeah, this is the dimension 26 representation of that. So, my question is, this is the open orbit is the new cone of this representation. Yeah, I can express it.
Okay, yeah, let's talk about that then. Okay. All right. Okay, so let's just quickly recap. So we have the space of smooth functions. We've identified this as an induced representation. There's some character prime out over here. I don't want to worry about that too much. Before we had the stabilizer down here, but now we know what the stabilizer is. Sorry, I want to set this up for for parabolic induction first. Okay, so we can do transitivity of induction. The stabilizer of the line, this is TH cross Q, the B3 parabolic. And then the stabilizer of the point, we have a expression for that above. And then let's look at this induction on the inside. Okay, so the action of Q cross, yeah, let me say it like this. So PH cross Q, right? This acts transitively on the line, okay? And then the stabilizer of X naught, it is whatever that thing is above, but now we can sort of reverse what we did before and identify this induced representation back with just a space of smooth, compactly supported functions. Now realized on F cross the orbit of X naught. All right, now we can finally go back and put everything together. So we have one to compute com of V we found that this was isomorphic to a TH Hom of C smooth compactly supported function on omega 0 into pi. Oops. We've now rewritten the space of smooth compactly supported functions as an induced representation. Some chi prime, then we have a parabolic induction And then we have this space of smooth functions on F cross. Let me, just for the sake of time, let me sort of skip over the details of this step and just give a reference. So there's this work, there's this lemma in Karasiewicz from American Journal from 2006, and this is lemma lemma 9.4. Okay, so let me make a few comments and then I'll sort of describe what's going on. So we're looking at this Hom space, pH homomorphisms, from some complicated induction of a space of functions on F cross into chi. Okay, now the TH, it's commuting with G, and so it doesn't really interact with the induction in a substantial way. And so basically what this lemma in Karasiewicz is saying is that to calculate this Hom space, we can sort of work inside of the induction just with the smooth compactly supported functions on F cross. And then if we're looking at maps from the smooth compactly supported functions on F cross to chi, which are T-module homomorphisms, we really just need to compute chi isotypic space. And for this, that is just a one-dimensional space isomorphic to chi itself. Sorry, I should have said the chi isotypic quotient. Okay? And this lemma by Karasiewicz is basically saying that you can pull that through the induction. And so the output of all of this will be the following Hom space. So there's this chi prime. We get this induction in Q. Oh, sorry, no more chi prime. We see this degenerate principal series. Okay, now I've been a little careless with characters and things like that. Everything works out so that this becomes normalized induction. So, big theta of chi linear dual, this becomes isomorphic to the linear dual of this degenerate principal series. Sorry. Sorry, the linear dual of the big theta of tau injects into this. Okay. And now from this, one can conclude that the degenerate principal series surjects onto big theta. All right. Okay. That will be all for this week.